This is part 231. Line 20c Astrochemistry, Infrared Spectroscopy, Molecular Energy, ICES Wow Seti. There's the alien radio signal, May 15, 2012. So I googled 1.2727 in the word NASA. This data was collected and compiled at the NASA Ames Research Center, Moffett Field, California. Any use of this data should recognize the parent publication. From D.M. Huggins, S.A. Sanford, L.J. Almadola, and A.G.G.M. Thiens, Mid and Far Infrared Spectroscopy of ICES, Optical Constants and Integrated Absorbances, the Astrophysical Journal. And that's from astrochem.org. So mid and far infrared spectroscopy of ICES, optical sense, Okay, laboratory spectra through the mid-infrared, this to this and that to that, have been used to calculate the optical constants N and K and integrated absorption coefficients A for a variety of pure and mixed molecular ices of relevance to astrophysics. The ices studied were H20, CH30H, CO2, OCS, CH4, CO2 plus CH4, CO2 plus OCS, CO plus CH4, CO plus OCS, O2 plus CH4, O2 plus OCS, N2 plus CH4, N2 plus OCS, H20 plus CH4, H2O plus OCS, and H2O plus CH3OH plus CO plus NH3. In addition, the measurements have been extended through the far infrared, that to that, for H2O, CH3OH, and H2O plus CH3OH plus CO plus NH3 ICES. Oh, there's keywords. Okay. So next I'm going to Google molecular ICES, and that's from adsabsharvard.edu. Astrochemistry from Wiki. Astrochemistry is the study of the abundance and reactions of chemical elements and molecules in the universe, and their interaction with radiation. The discipline is an overlap of astronomy and chemistry. The word astrochemistry may be applied to both the solar system and the interstellar medium. The study of the abundance of elements and isotope ratios in solar system objects, such as meteorites, is also called cosmochemistry, while the study of interstellar atoms and molecules and their interaction with radiation is sometimes also called molecular astrophysics. Sorry. The formation, atomic and chemical composition, evolution, and fate of molecular gas clouds is of special interest because it is from these clouds that solar systems form. So obviously these videos are talking a lot about the solar system and how it was created. So the PDF is for Molecules, ICES, and Astronomy. It's from chemucl.ac.uk. From D.A. Williams, February 2007. Over the past 40 years, about 140 distinct molecular species have been detected in a wide range of astronomical locations. The next thing that comes up is surface functionalization by low-energy electron processing of molecular ICES. From Lafosse, Burton, Hoffman, and Azura, University Paris. Abstract. Low-energy electron processing of condensed molecular films, also called ICES, is an efficient method to induce functionalization of a substrate and thereby to modify and adjust its electronic and chemical properties. This method takes advantage of a resonant mechanism specific to low-energy electrons by opposition to photons. The dissociative electron attachment, DEA, the key process allowing the chemical selectivity to be directly and easily controlled by the kinetic energy of the processing electrons. The functionalization procedure is described and illustrated by high-resolution electron energy loss spectroscopy, HREELS, results on the induced anchoring of CH2CN, organic chains on synthetic diamond by electron irradiation at 2 eV of condensed acetonitrile. The range of application of the proposed functionalization method is worth to be extended to other organic and inorganic interfaces such as organic layers on metallic and semiconducting substrates. And there's the keywords. And some ScienceDirect.com. Here's a graph here. And take a look at that. Right there. Principle of the experimental method for substrate functionalization by low energy electron processing of molecular ICES. A film of molecules is prepared by vapor deposition on the passivated substrate, cooled down to minus 30 K. I think that's a minus, I could be wrong. And irradiated using electrons of tunable energy 0 to 20 eV and dose. 10 to the 15 minus 10 to the 16 E divided by mm squared. The substrate is then warmed up to 400 K so that all the physio-orbed material desorbs. The result of the electron writing procedure is probed by real spectroscopy, and the chemiscope organic groups are identified by their vibrational signature. And here's a equation there in numbers. So it's number 3, proposed mechanism for diamond functionalization by electron irradiation at 2 eV of condensed isotronyl CH3CN. Step 1, DA process leading to the formation of hydrogen radicals and anions. CH2CN. Step 2 is depassivation of the hydrogenated diamond surface via recombinative abstraction of H atoms by H radicals, leading to the release of molecular hydrogen and the creation of an active site on the substrate. Step 3. Simultaneous bonding of CH2CN chains by their C or N terminal atoms on vacant dangling bonds of diamond and electron ejection in vacuum or flowing through the substrate. Corresponding author is from Paris, France. It's from ScienceDirect.com. Another PDF file came up, EUV, VUV, photolysis of molecular ice systems of astronomical interest, and this is from ntrs.nasa.gov in their archives, and it was published in 2006 by C. Wu. Violet EUV and vacuum ultraviolet EVUV photolysis of molecular ices relevant to the cometary type ices and icy satellites of planetary systems. J-Chem Physics, low energy electron stimulated production of molecular hydrogen from amorphous water ice. And there's the scientists for that. And it's from the Center Pacific Northwest Laboratory in Washington. Okay, we have observed via quadruple mass spectrometry, QMS, stimulated production of D2H2 during low energy 5 to 50 eV. Electron beam irradiation of D2O, H2O, amorphous ice. The upper limit for the D2H2 production threshold is 6.3 plus 0.5 eV, well below the first excited state of condensed water at 7.3 eV. The D2H2 yield increases gradually until another threshold is reached at 17 eV, and continues to increase monotonically within experimental error up to 50 eV. We assign the 6.3 eV threshold to D minus H minus plus D2O, H2O to D, I don't know how to say that. So look at that equation there. Condensed phase, primarily surface reactions, that are initiated by dissociative attachment. We associate the yield below 11 eV with the dissociation of Frankel-type excitons and attribute the yield above 11 eV mainly to the recombination of D2O plus or D3O plus with quasi-free or trapped electrons. Exciton dissociation and ion-electron recombination processes can produce reactive energies of DH atom fragments, or D2H2, directly via molecular elimination. The importance of D plus H plus interactions increases at 17 eV dipolar threshold, and at energies of that, where multi-hole and multi-electron final states are energetically accessible. And that's from jcp.aip.org. Okay, so we'll go on to our next video, which is 20D.